Good morning. Today is December the 2nd. Today is the first week, finished this first week of the class after the evaluations. Today, I would like to go on with the study of plane stress, but instead of trying to solve it analytically, we're going to use finite elements, okay? There are several options to do this discretization. The simplest is the one that we are going to be using in class. And it's discretization, which uses a linear distribution. Similarly with the distribution that we employed for the bar, for the actual displacement of the bar. The difference in this case is that this is a 2D problem. See, so I wanted to get up to this point as far as the details of the finite elements. So you will be working with 2D problems in this subchapter, right? And after completing this experience for you, we will go to ANSYS, the use of the program ANSYS to solve very complex structural problems, okay? So I wanted you to have a first-hand experience on using discretization, but not only in 1D, but in 2D problems, okay? We don't have the time. I wish we had more time to go into, so you have an experience discretizing a 3D problem, like a solid, but we don't have the time. But at least you have a decent idea. You can compare what happened in 1D and also in 2D, which is something that we're going to do. And this 2D experience, we're going to be using only in one plane. Okay, for example, we don't have two plates like this. Okay, so we have only one plane, one single plane, and in this plane, we are going to do the discretization. So I'm going to explain a little bit about that discretization. It's quite similar. The only difference is that we need to increase the size of our matrices. Basically, that's it. Okay, and it's a nice experience to know what happens when we have not only one, but two displacement to worry about, because this is a 2D problem. And then we're going to present an example. For those of you who just joined us, I posted this example in the announcements of the SID web, so you can download it. It's very similar to the file that I posted 3 weeks ago. So to identify it, I put it a V2 in the name and the last part of the name, so you can recognize them. So it includes just minor differences, but I think it's better to have a good version of that. At the end of the session, I will explain or answer questions about this assignment if there is issues, there is problems about it. Okay, so let's do it. Okay, we are working with plane stress problems. Well, here. Genesis, can you see my screen? My PowerPoint?
Yes, sir.
Okay, thank you. So we studied already how to apply minimum potential energy in the case of the bar and beams. And one of the most interesting applications of this minimum potential energy is the fact that we can follow this very general procedure in order to have equivalent forces for the general case. Okay, so you have the distributed force, and you're gonna follow this procedure. Basically, you multiply by the vector of the polynomials that we employ for interpolation. You integrate the distribution, and you get equivalent forces. Okay, that's so simple as that. Okay, so you can have any distribution. So in this homework number whatever 4, I think, you have to do it, and we are using only concentrated forces. You have to do that for one concentrated force, which is in between two joints. Okay, so let's see where you can do it, and after that we are ready to start the plane stress problem part of this class. So in this case, we are working with, as we said in this slide last Monday, this plate supports forces only in the same plane of the plate, okay? So this is what we call plane stress. See, on the contrary, when we use plate bending, this is something that we studied in ship structure, but we are not going, we don't have the time, we are not going to work with plane bending in this class in finite elements, okay? We are not going to do that. But it's a good idea that you can recognize the difference, okay? When we have linear problems and you have both, what you can do is you can solve one, solve the other, and you simply superimpose results, okay? In general, if you have tension forces, okay, so you have the plate and you apply tension forces. In general, I think results are reasonable. When you have compression and also lateral force, you have to be careful. If the compression forces get close, in general, close to critical stresses, remember, to those that produce buckling, then the results are completely off. But if the in plane, the compressive forces are decent, then the results are okay. What I'm saying is that if you have a plate, you apply a force, compressive force, which is not very large, not very close to the critical value, and also you have lateral forces. In those cases, you can calculate both effects, in plane, bending separately, and then you can superimpose. So it's okay. So in this class, we have time only for this problem, for plane stress. That's all. Here we have only forces F in the X direction, in the Y direction, and also you can have shear effects, but only in the plane. So it's like having a force sub X, Y. That's all what you can have, okay? And which is interesting in this with this example or with this topic is the fact that, say, you have a plate, you have a point, and that point can move in the X and also in the Y direction. Okay, so far, when we dealt with bars, okay, you have a bar, you apply an axial force, and each section could move axially only. When you have a beam, you have very long element, and you have a vertical force. This section, every section could move in the vertical direction and rotate. So with one single function, v of x, we could solve the problem. In this case, we cannot do that. We need two functions to describe the solution. That's for every point in the plane, as you can see in this slide, you need to calculate how much moves in the X direction and also how much it moves in the Y direction. Okay, so it's a little bit more complex. And that's why I wanted you to take a quick look at that. Okay, this is just a review. This is the way we define strains is the same as we did in ship structure when we work with plane bending. So we have epsilon x, epsilon y, gamma xy. And also we will be working in the linear elastic range. So strain and stresses are related by, in this case, isotropic materials with two constants, Young modulus and Poisson ratio. And in this case, it's always a good idea that you remember G, how to transform E and nu to G. This relation is similar to this one, but it's just putting this matrix of constants on the other side, okay? So we express the stresses as function of this matrix and times epsilon, okay? And this matrix, people, we're going to need it in a couple of minutes, okay? So please, let's insist on this, okay? This matrix, okay? We can write this, for example, as something like this. So this is the vector sigma. We have three components of the stress tensor that we need, and this is related to the vector of the strains, epsilon x, epsilon y, and gamma xy. Okay, and this matrix that relates sigma and epsilon, we call it D. So all of this is what in this class we're going to call matrix D. Okay, and we're going to need that in a minute. This is just, I insist just to remind you, some of these are probably new. Remember, in this case, what I'm showing you here is the equilibrium. So when you analyze equilibrium, you make a cut at a certain position and then a different cut. So there is a distance from this cut to this one here, okay? It's different. In some cases, we use this figure in order to show, for example, the sign convention. And in that case, you show on this cut, sigma x points to the right. And in this cut, the same sigma x points to the left. But there are two different cuts. No, it's the same. It's just showing you the sign convention. This case is different. In this case, this cut is not this one. So you make a cut here and you move to the right, okay? How much you move? You move dx. Similarly, in the other direction, you make a cut here at the position y, and then you move in the y direction. How much? dy. And then you make another cut. So you define a differential element, which is arbitrary. And for that arbitrary element, we try to solve its equilibrium. So if we say that in general, we pick one element and we are sure that this arbitrary element, because we're not picking this specific node, we just pick one arbitrary element and we are able to solve its equilibrium. That means that if any element is in equilibrium, that means that the whole plate is in equilibrium. Okay, and you recognize that that's a process that we do quite often. So here we have equilibrium in the x direction. So we multiply stresses times area and then simplify, and this is what we get in the x direction. We can do something similar. This is for the y direction. And in the case of the moment, this is what we obtain. And this is something that you recognize from solid mechanics, okay? So in the case of plane stress, okay, it's typical. Instead of trying to calculate directly for sigma x, sigma y, and tau xy, we try to solve that using another function. That's what we call the 80 stress function, okay? So the 80 stress function is defined in this way. So it's just another function and allows us to express the problem in a different way. So instead of trying to calculate sigma, I'm going to calculate phi. That's all. Since we have a very concrete definition for sigma, and we have an equation, equilibrium equation, to find sigma, we need to go to define a relationship from sigma to phi. And that's what we do here. And the way it is defined, you can replace those definitions into the equilibrium equation that we just mentioned. And you know, and you notice, and you can check that those equations are satisfied exactly. So if we accept this definition for phi, we don't have to worry about equilibrium anymore. This is just what we need. Now, if we have satisfied equilibrium, how do we calculate phi? Well, the thing is this, okay? We have two functions, okay, u and v, to determine the displacement of any point of the plate in the x and in the y direction, okay? The problem is that with these two functions, we have three, okay, three terms of the stress tensors, sigma x, sigma y, and gamma xy, 2, 3. So it is possible that in this calculation, we introduce some extra terms. And to avoid that is what we define a compatibility equation, okay? So if we start by du dx and dv dy, and we assume that u and v are functions which can be differentiated without any problem, are continuous without any problem. And that's what we expect for the displacements in a plane, right? In a plate. And we differentiate these twice with respect to y, this twice with respect to x. We can express this result in this way, okay? And to go from the left to the right, okay, what we need to be certain is that we can change the order of differentiation. And we can do that simply by saying that u and v are differentiable and also continuous. You can remember that from your calculus of several variables, okay? So that's an identity. But here we see that du dx is epsilon x, and this is epsilon y. This is gamma xy. So when we started simply by two functions, which are continuous and differentiable, are now a relationship which relates epsilons and gamma, which are strains, okay? Here, using Hooke's law, we can replace this in terms of sigma. And sigma, we can remember the definition of the 80 stress function here. We can do the same for the second term. We can do the same for the term from the right-hand side term. And we can make some cancellations. And this is the result. So the fourth derivative of x twice the mixed derivative and fourth derivative of y. And they combined has to be equal to 0. This is a compact way to do it. Okay, so this is the typical way that we solve plane stress problems in general. We try to solve this equation, okay, trying to find values of this function in a certain domain. And then using the definitions that we presented previously, we may calculate sigma x, sigma y, and tau xy. Okay, so this is the continuous version of this thing. We're going to do that, but with this discretization scheme, and that's finite elements. Okay, so let's do finite elements to solve this problem. Is there any questions so far? I don't know, is there any question, people?
Yes, Doctor. Good morning, I'm Mr. Jimenez.
Okay, go on, Jimenez.
Can you back the slide number 3?
Let's see if I can go back. This one here, yes?
Yeah. For U and B is the displacement on the plate, right?
Yes.
For one point. This displacement generate any curvature on the plate?
Any?
Any curvature?
Yeah, but remember that the plate is like this, right? And you apply a force in this direction and a force in this direction. So if you see the plate, any point, okay, because you apply a force to the right, a force to you, a shear force like this. So the only new position that a point can take is in the same plate. You are not applying any vertical force. This is not what we are doing. This is bending. We are just keeping all the time in this plane. So we don't have any curvature like this. We are always flat like this. So there is no curvature like this.
Yes, doctor. Thanks.
No problem.
Another question.
Yeah, go on.
For the last slides.
Let me go back. Just a second. Let me move here. Go on.
For the ID function, it's a linear solution, homogeneous, right? But
yes, it is linear and homogeneous. Yes.
Yeah.
And
how many boundary conditions have for each point?
This is as we have applied several times in our course. I'm just going to say this. Okay, this is a fourth order. Okay, linear EDP. This is partial. Okay, and it's homogeneous in general. Now, the equation is homogeneous, right? But in general, we have to apply forces. So when you apply a force, okay, because you apply a force, in that point, you can have, you must have a boundary condition which is non-homogeneous, okay? So in general, the problem, that's the combination of the equation and the boundary conditions, the two things together, that's the final problem, is non-homogeneous. Okay, so the equation is homogeneous, but the boundary conditions will not, because you will be applying a force. If you have a plate like this and you apply no force, I mean, there will be nothing. It's just the plate, that's it. So if you have the plate but apply a force, in the point when you apply the force, you have to set a boundary condition. But that's not, it's going to be different than zero. Okay, so as you say correct, this is a fourth order linear. So if it is a fourth order, you need two boundary conditions for every point along edges. So along every point, in every point of the boundaries, which are the edges of the plate, you need to specify two conditions.
Okay, doctor. Thanks.
No problem. No problem. Okay, now let's stay. So we're going to use discretization using what we call it's CST. Okay, I'm going to explain that in a minute, but this term mean. Okay, CST, constant strain triangle, is the simplest case. Okay, so let's do it. Okay, so we are trying to find approximations to a 2D problem. Okay, so let's suppose we have a plate like this. It is not a rectangular plate in general. This is X and this is Y. This is a flat plate, okay? So what we have to do is we have to, remember, we have to partition, okay? And of course we can partition this plate, we could partition simply by using fourth corners. That's it. And we could go on. Yeah, we can do that. But there is a simpler way. See, a much easier way. And this is the way that we're going to use it. And the way we're going to be doing is using triangles. So we have this is going to be element 1, and this is going to be element 2. Now, in each element, as we said before, we need to consider 2 functions. So we are going to partition the domain using triangles. Define it by its 3 corner on, I'm sorry, it's the other way. It's the 3 joints on the corners. Okay, you can imagine that you could define an interpolation for every triangle using not only 3. For example, we could develop an interpolation using the values of the function at the corners and also at the centroid. In that case, we will have 4 points to define our interpolation. Now, the simplest way is to do this. First, we partition this flat plate into triangles. And then for every triangle, we're going to do an interpolation. And it's going to be a simplest interpolation using the joints located at its corner. That's all. So that's the simplest way to do it. Okay, now we have to keep in mind that we need 2 functions. We need U and we need V. Okay, let's see if we can, oh, shoot, duplicate, is this, and is this. Let me duplicate this. Okay. There. Okay. So in every element, we are interested in 2 functions. Okay, and those functions are U, which depends on, and also V, which depends on X and Y. Now, these functions that we're going to develop are for every element, But the thing is that in every point, we're going to find 2 values, U and V. And from those U and V, we can develop an interpolation in every element. Okay, so it's a little bit complex, but the process is the same that we did before. So we have three conditions. Okay, we can develop an interpolation, a polynomial interpolation in every element. But we have to be certain that since it is an interpolation, we recuperate the value when we evaluate this function, this polynomial, at every joint. Since we have three conditions, then we can define three constants. Okay? Since we have three conditions, okay, we can find three constants. So the interpolation scheme will be the following. See, okay, so let's suppose I have an X, Y plane. So I have a triangle here like this. These are my three joints, right? So in every element like this one, if I know the value here, here, and here, we can do an interpolation in S in this element. But this interpolation has to be applied to find U and also to find V. But what we do is we use the same interpolation for those two functions. Makes sense because they're so similar. The only difference is that the values at the joints are different. So in one point, for example, you could find that this point moves in the X direction, but it doesn't move in the Y direction. Or you can find that this value moves in the X direction in the positive sense, and in the V and the Y direction, it moves in the negative sense. There is no problem. But after you find the three values for U or the three values of V, you can interpolate in this element. So since we can find only three constants, the interpolation are going to follow this scheme. So UN inside this element could be interpolated following these three constants. So it's going to be a constant A1 plus A2X plus A3Y. So you can see that this is a linear interpolation. That's all what we can do. Why? Because we have three joints. So we have to force it, as we said here, we have to force this function to recuperate the value here, here, and here. So let's call this joint in general, let's call this joint I. This joint J, and this joint K. So we have to find is that U at joint M. Okay, this M could be I, J, or K, has to be equal to U, M. Okay, so M could be I, J, or K. So we're saying is that we take this function, we evaluate it here. So you know this position. So you know Xi, you know Yi. So you put here Xi, put here Yi. And the result of that has to be equal to the value of this function at this point. And that's UM. So you have three equations because we can do this to evaluate the displacement here, here, and here. So we have three equations, three unknowns. We can solve for A1, A2, and A3. Okay? And this is exactly what we did in bars. Okay, so let's show graphically what we are doing. So what we're doing is this. So we have something like this. And let's suppose that I know the value here. So the value here will be something like this, for example. So the height, this will give you UI. You know the value here. For example, let's suppose that we have a larger value. This is UJ. And let's suppose that we know that this is UK. Okay? So this function, linear function, okay? Since it is a linear function, it will generate a flat surface between these 3 points. Okay, so this, the function that I just showed you, generate something like this. This is straight from here to there. So this is the interpolation. And this is flat because the polynomial is linear. Okay, and you immediately tell me, what would happen, people? What would happen if, because of the load, this were not a linear distribution? And the answer is, there is an error. How do we reduce this error? Making elements smaller. So when you have a curvature, you can describe them with little straight lines, and you can follow the curvature in an acceptable way. But you have to be certain that there is this approximation and the other approximations that we have made. It's a source of possible error. We have to be aware of that. Finite element, it's a very nice tool, but it's not completely precise. That's the idea behind these exercises, manual exercises. Okay? It's an approximation. Now, what happens with the next element? Okay? Okay? Now, let's suppose that we have these two joints, and I have another joint here. Okay, this is a different element, and we already know this value and this value here. So we are going to find a different value. Let's suppose that we have value like this one here. Let's call it UN. And in this element, we apply the same formulation. That is, we generate with this, and this value, we generate a little flat surface. And that flat surface will give you something like this. And this is also another flat part. So we have a little flat, and that's what you see in el Parque Forestal. You see a dome, and you assume that it has curvature. It's not. It's composed of little triangles, and every one is a flat surface. But if they are small enough, you can describe adequately the curvature. And this is what we're doing. Okay? So to complete and go to the first break, okay, we can do this. This is an equation. And we can try to find A1, A2, and A3. And these are functions of this is UI, UJ, and UK. And in here, I have X and Y for I, J, and K. Remember, what we're doing is this. We are taking this expression and we evaluate it here. So instead of X, I put XI. Instead of Y, I put YI. I do the same for the other and for the third joint. So this is the equations that we have. And from here, we can get A1, A2, and A3. And then we can go on with the procedure. Let's take a break to recuperate my voice, okay? 5-minute break.